Okay, good morning, everybody. So it's Tuesday, May 19th, which means that yesterday everyone took their AP Environmental Science exam, so I hope that went for everyone. But today we're going to be, let me full screen scenes. We're going to be covering environmental geology. This is, I didn't plan on this to have it line up, but yesterday was the 40th anniversary of the Mount St. Helens eruption, which happened May 18th, 1980. Um, it was where Mount St. Helens, a mountain in Washington state, erupted. And it was such a devastating volcano that the height of it actually blew the top off the mountain, and the height of the mountain was reduced by a little over 400 meters. So it was a massive explosion. So rather than it coming to a peak at the top, it now has a bowl at the top of what you would expect with it. We're going to talk about environmental geology. So to outline what this is, we're going to talk about tectonic processes, different types of rocks and minerals, economic geology and mineralogy, so strategic resources, environmental effects of resource extraction. The major one with that is, of course, mining. We're going to talk about restoration attempts, and then conserving geologic resources and geological hazard. So we have a pretty dynamic planet. All right, it's we kind of know, anyone that's taken Earth space science or anyone that's seen a picture of a cutaway of the globe has seen that it's layered. Right? You have a core, which is an interior composed of dense, intensely hot metals, and this is what generates the magnetic field that covers the Earth. And the magnetic field is what is responsible for shielding us from a lot of the solar winds that happen and some of the charged particles that's thrown off by the sun. The mantle is a hot, pliable layer surrounding the core. It's also less dense than the core. Mostly, so the core is mostly made out of metals, right? The biggest one being iron. The mantle is slightly less dense than that and sits on top of it. And then the crust is a cool, lightweight, brittle outermost layer, and that's what floats on the top, and that's that. So looking at it, here's the scale. You have the inner core, which is solid, the outer core, which is semi-solid. So it's more of like, if you've seen how there's scientists that they move lava, like in movies, lava is like water, but it's actually more like a sort of like thin, I guess, thin peanut butter. So like jelly, something like that. Like it's very soft, but it's also not like, very viscous like water. And so you have this outer core, the mantle sits on top of that, and then you have the crust all the way on the outside. So we'll go through tectonic processes. The upper layer of the mantle contains convection currents that break overlaying crusts into a mosaic of tectonic plates. Again, this isn't stationary. These cause these tectonic plates to kind of slide slowly across the Earth's surface. And ocean basins form where continents crack and pull apart. Magma is then forced up through those cracks in oceanic crusts and form mid-oceanic ridges. A really good example of that is Hawaii. Hawaii is a volcanic island, so it is fresh rock that was then colonized by lichens and organisms similar to that soil, and we could still see that volcanic activity to this day, forming new parts of the land in Hawaii. So here's kind of a picture of the tectonic process. So you have a magma chamber that's kind of stored below a what we would call volcano, or near the edge of some sort of vent for this magma that would come out and cause a lava flow, which then causes a sediment deposit. And then you have the sediment deposit can make its way through kind of these tectonic plates. The tectonic plates move apart, causing these openings where magma and hot mineralized water meet, and this can cause a mid-ocean ridge. A lot of times these are mapped out. If you ever look at an ocean map. So when I was in the Navy, they used to have undersea maps, and you would spread those maps out. Like, and then the way that it worked is the maps were kind of these. I don't want to say they were transparent, but you could set them out onto this table, and then you were able to mark on it, and there was a light that kind of showed the position of the ship based off of either GPS or based off of taking data like time. And there's a thing called the pit sword, which hangs out the bottom of the ship and records the speed of the ship as water pass across it, and the direction and all of that stuff. And all those inputs kind of lead to the position. And then on the map, it looks like you're looking at a topographical map of land, but it's all inverted. So if it says 200, that means that that spot is 200 meters deep. And you use that because if a ship is sitting on the bottom of the ocean, that's not good. So you use that, you know, the depth of your ship, the draft. So one of the ships that I deployed on, the draft was 27 feet. Another one I deployed on, it was 21. Another one was 18. So you have these varying depths. Some of the big cargo ships sit around 40 to 60 feet deep and can even go deeper than that. And you want to try to navigate through areas where that's not the case, or where that you're not going to run aground. And so these mid-ocean ridges are mapped out quite a bit. They use sonar and bounce that off the floor, and it gives depth readings that they use that to upgrade charts. So earthquakes are caused by grinding of the plates when they slide past each other, and there's usually a slip involved. Mountain ranges pushed up at margins of colliding plates. A really good example of this is the Himalayas. Himalayas are a collision between two plates, and I remember back when I was in school, they were saying that the Himalayas are rising, and that's possibly the case, that they are increasing. It's just the process is so slow that we're not going to see a major movement. Like, it's not like you're going to climb Mount Everest, and then 5 years later, you know, you're going to climb Mount Everest and be hundreds of feet higher. When ocean plates collide with land masses, the continental plates will rise up over the seafloor, and oceanic plates will subduct down into the mantle. This is kind of how they slide past each other. You know, if you take two sheets of paper and you press them again, like they sit side by side on a desk, and you start to push them together, eventually they're either one's going to pass over top of the other, or they're both going to start to move upward. And this is the same way about how ocean plates kind of work. Deep open trenches mark subduction zones, the most famous one being the Marianas Trench and Challenger Deep, which is the deepest point in the ocean. So looking at tectonic processes, here is all the plates. So you have the North American plate. Here's the Aleutian Trench, where the Aleutian Sea is at, and the Aleutian Islands. The South American plate, you have the Andes mountains through here. You have a very low point along here, and then you have the San Andreas Fault. Then you have the African and Arabian plate going through where the Suez Canal is, the Eurasian plate, and then you have the Indian Australian plate. This is the Himalayas, so this arrow shows the direction in which the plate is moving, so it's pressing up against the Eurasian plate. The Marianas Trench is over here where the Philippine plate is. So you can kind of see like how all of these interact and intersect. And then the Antarctic plate, it looks like it's massive, and it is pretty big, but you have to think that due to the projection of this map, it's been kind of flattened out. You know, it's like in this picture about how Alaska looks a lot smaller, but in reality, it's massive. So Pangea, I think we've all kind of heard stories of this. Geologists suggest that several times in Earth's history, most or all of the continents gathered in to form a single supercontinent, Pangea, surrounded by a single global ocean. And you can see this in how some of these continents kind of match up a little bit, how Africa kind of fits in really well with North and South America, a lot of with South America, and they kind of went together. And then you have this large ocean. And this has some of the evidence that supports it shows that there were some ferns that exist, or fossils of ferns that existed in North America and Greenland, even though the climate in Greenland can't support those ferns. It just kind of shows that this place was once connected, then separated, and then after it separated, those species ended up dying off and then fossilized. So rocks and minerals. A mineral is a naturally occurring inorganic solid element or compound with a definite chemical composition and regular internal crystal structure. A rock is a solid cohesive aggregate of one or more minerals, and each rock has a characteristic mixture of minerals, grain sizes, and ways in which the grains are held together. This is why minerals tend to be more valuable, is because they are kind of this singular composition. So, for example, quartz. Quartz can be valuable. It is quite abundant. Like if you have a watch that ticks each second out and uses a battery, that is a quartz watch. And so if you ever see like an Apple Watch, for instance, has a quartz oscillator on the inside to help it keep time if it's not connected to your phone or the internet or GPS. Like right now, I'm wearing the watch that I'm wearing is a Speedmaster X33, and it's quartz powered. It has a battery in the back of it. It uses quartz where it passes an electrical signal through it, and that vibration keeps the time. And so there's different types of minerals. Diamond, for instance, is a mineral that's comprised of just straight carbon. A rock, on the other hand, is a mixture of a lot of these. So in order to extract minerals from those rocks, there is a process you have to go. So looking at rock types, there is a rock cycle, which is the cycle of creation, destruction, and metamorphosis of rocks. There's three major rock classification. There's igneous rock, sedimentary rock, and metamorphic rock. And then this picture kind of shows what they look like. When we were in class, I borrowed from the earth-based science teacher a handful of rocks and brought those around. And well, very few people looked at them, but you can see the different types based off of what's happening with rocks. Looking at igneous rock, it's the most common type of rock in Earth's crust. It's solidified from magma extruding onto the surface from volcanic vents, and they cool quick. Start this sentence over. Quick cooling of magma produces fine-grained rocks. So if you ever heard of basalts, the slow cooling of magma can also produce slow-grained rocks like granite. Granite's like, if you ever watch HGTV, it's like the most basic, like, I want to redo my kitchen, I'm going to get it made out of granite. So weathering of rocks can be mechanical, and this is the physical breakup of rocks into smaller particles without a change in the chemical composition. Then there's chemical, which is the selective removal or alteration of specific components that lead to weakening or disintegration of the rock. So like oxidation, for instance. Reddish rocks a lot of times have oxidation. They contain a lot of iron. Then there's sedimentation, the deposition of loosened material. Looking at sedimentary rock, this is deposited materials that remain in place long enough or are covered with enough material for compaction and may again become rock. You can kind of think of this as if you were to take a compound and place it into, like, let's say a vise, or there was a when I was getting if you get a biology degree, or you are pre-med, pre-dental, or chemistry major, you will have to take organic chemistry. And in that, there's a compound that you make. You take your chemical sample, and it's a powder, and you put it into this, you put that and then this other powder onto a piece of paper. You dump that into this thing that's made out of 2 bolts and 2 nuts that connect it, and you tighten it down with a torque wrench that slips at 35 Newton meters. And then when you undo the bolt and you look at what's on the inside of it, it's actually this, even though you put in kind of this white powder, it comes out as this clear kind of stone type thing. And that is what happens with sedimentation. You have this loose deposited material, and if given enough time and compaction, it eventually compresses itself to become a rock again. So it's formed from crystals that precipitate out of or grow from a solution. So shale is an example of this. Sandstone is another one. Tuff. Metamorphic rock. This is pre-existing rock that's been modified by heat, pressure, or chemical agents. And chemical reactions can alter both the composition and structure of rocks as they are metamorphosized. They're changed. Marble is an example, which it comes from limestone. So limestone being very common here in Indiana, especially southern Indiana. Quartzite, which is made from sandstone. Slate, which is made from mudstone and shale. So economic, geology, and mineralogy. We're going to look at metals. So metals consume the greatest quantity by world industry. So the most metric tons annually is iron. If you have something made out of steel, stainless steel, anything like that, it's mostly made out of iron. Then you have aluminum, which is a pretty good chunk. This is used a lot by the airline industry and the space industry, since it is pretty rigid, but it's lightweight. So for example, like entry-level bikes, a lot of times are going to be made out of steel, and then a step above that, it's going to be made out of aluminum, because they're lighter weight and you can kind of bend them to be really stiff. And then the top end bikes are made out of carbon fiber. Manganese is another one that's widely used. Copper and chromium tends to be pretty high. And the reason that copper is so high is because we use that as a conductor. In some houses where it's they're manufactured a little bit lower end, instead of copper, it uses aluminum wiring. It's actually really common that in some abandoned houses, people will break in and strip all the copper out of the walls. Nickel is another one. So if you've ever used surgical grade stainless steel, that has nickel in it. A lot of like lower end jewelry that is very shiny will have nickel on it. Some people have an allergic reaction to it, and you can tell that if they wear earrings and stuff in their, or the bracelets, and they get a little bit of swelling. It's contact dermatitis that comes from the nickel. So non-metal mineral resources, sand and gravel. So brick and concrete construction, paving, sandblasting, and glass production all use sand and gravel. My computer runs off a microprocessor, which is made out of silicon sand. Limestone is another one. Again, this is a big industry in southern Indiana. It's used for concrete and stone building. This is why a lot of the sidewalks around this area tend to be like a really bright white color, and that comes from crushed limestone. You have evaporates, so gypsum and potash. Potash is used for a lot of metal extraction. And then sulfur, we use that to make industrial sulfuric acids. So strategic metals and minerals. Of the 80 industrial metals and minerals, between 1/3 and 1/2 are considered strategic resources. So a country uses them, but they cannot produce them. Considerable capability, or considered capable of crippling nations' economy or military strength if supplies were to be cut off. So this is where the strategic part comes in. Second. Sorry about that. Many less developed nations depend on steady stream or steady mineral exports for foreign exchange. A big example of this, like I said before, is quartz. And the reason, so why is quartz so big? It's not like watches are everywhere, but they are in the form of timing. So, for example, I do a lot of amateur radio, and I use a digital mode called FT8. With FT8, your computer clock needs to be accurate to within 1 second, because it's a 15-second transmit, 15-second listen cycle. And then with FT4, it's 7.5 seconds transmit, 7.5 seconds receive. So because it's so fast and you're doing it so quickly, being off by a couple seconds means that you're either going to send late and no one's going to hear your signal, or you're going to receive late and you're not going to hear anyone's signal. So a really common thing that they always say is, if you're running FT8 and you're not able to decode anyone's signal, check your computer clock and see if it's accurate. And a lot of militaries kind of do the exact same thing. Having perfect timing is how GPS works. And you can watch videos on how GPS actually works, like the logistics behind it. Um, there are numerous satellites that run off of that need to have accurate time, and because of that, quartz becomes this extremely valuable mineral that a lot of places need. So here's the strategic metals and minerals. So bauxite being the biggest, manganese being up there, chromium being a little bit less, tin, cobalt, radioactive cobalt is used quite a bit in radioactive cobalt is used in X-rays. Tantalum, palladium is used in a lot of circuits. And then platinum, the nice thing about platinum is that it is extremely resistant to corrosion. So for example, I have a molten block fountain pen, and that is extremely resistant to corrosion because it is made out of a resin, and then the metal parts of it are made out of gold and platinum, both of which are extremely resistant to oxidation. This is why stainless steel items will rust and corrode and end up with pitting. So if you look at the metal really close, you see these pits in them. But if you look at platinum, for instance, it doesn't get that same exact pitting. This is why gold-plated items are so valuable, because it protects the metals that are underneath with this layer, this thin layer of gold. So environmental effects of resource extraction. So mining is the big one that we kind of think about. So placer mine, hydraulically washing out metals deposited in stream bed gravel. Destroys stream beds and fills water with suspended solids. All of these processes you can see videos of online. So if you just go to YouTube, normally in class I would show them, but I don't want to have to exit out and load up a bunch of stuff and kind of waste some time. Also, my audio is not set up appropriately to listen because they're loud, but because the audio on YouTube videos are so loud, I just don't want to have to deal with adjusting it. So placer mine, so look these videos up if you want to see what this looks like. So placer mining is hydraulically washing out metals. Strip mining or open pit mining, this leaves large scars on land surfaces. This is where you just remove everything that you can. It also leads to what are called mine tailings. This is a major form of mining restoration, is following mine tailings. This can lead to some toxic runoff from these mine tailings, because obviously you're extracting materials that are not valuable. Underground mining, this is the most common one that we think of with mining. This can be very dangerous. You obviously have toxic gases that can build up, or you can rupture into gas pockets held within that rock. You're also inhaling particulate matter, which is just like debris that's dissolved within the air. You can think of it as dust. There's also obviously tunnel collapse. These are the big ones that kind of make the news. Tunnel collapse. So we're going to talk a little bit about restoration. So Surface Mining Control and Reclamation Act of 1977 requires better restoration of strip mine lands, especially in lands classed as prime farmland. This is difficult and expensive. A minimum reclamation costs about $1,000 an acre, while complete restoration can cost $5,000 an acre. 50% of U.S. coal is strip mined. Kind of back to this, something's wrong with my audio where it's clipping it. Second to adjust. It's my noise gate filter. Apparently the open threshold is too low to that. Okay, that's better. Oh, go back. So there, my master's advisor worked at the University of Tennessee when he was getting his PhD, and his PhD advisor, one of the research projects that he had was doing mine restorations, and they were just basically going along these mine tailings. They would take out a ton of plants, and then they would move along this little area, and they would dig a little hole, put the plant in it, recover that, and then kind of move on from there. But that was how they did this kind of reclamation process. There was an experiment that was behind it. He really didn't talk much about it, but at the same time, I really didn't ask. But I assume it was off of a federal grant. So processing, this is processing of the materials that we extract from the ground. So metals are extracted from ores by heating or treatment with chemical solvents. There's a video on periodic tables that talks about how they do this with the platinum group metals. So smelting is where you actually melt ore to release the metals. So you burn up all of this ore, and then kind of the extra debris that's within it will separate out. Sometimes you see them do this and they kind of scoop a layer off the top. That is a non-metals that are dissolved within it. It's a major source of air pollution. Obviously, it requires a lot of heat to do that, and that is a lot of energy. You also have heap leach extraction, which is crushed ore piled into large heaps and then sprayed with a dilute alkaline cyanide solution, which percolates through the pile and dissolves out gold. And then you have effluent that's left behind in ponds. Usually you see this right next to, or you see these ponds right next to these massive extraction piles. So conserving geological resources. A big part of it is recycling. This is why you see the We Buy Gold places. And the reason being is because if you take in an item, right? Let's say you have a gold ring, and you take that in and you go to get it recycled. It's actually cheaper for a company to purchase recycled materials than it is. It's cheaper for a company to purchase recycled materials than it is for a company to go through and extract and get fresh gold. Not only that, but it's just safer because you don't have people that are actually mining it. There's not as many chemicals that are involved. So it's recycling precious metals is a massive industry, and it doesn't matter what type of metal it is. Recycling is huge behind it. Aluminum must be extracted from bauxite by electrolysis. Electrolysis is really, really cool. It's a really cool process. Recycling waste aluminum extracts consumes 1/20th of the energy of extraction of raw ore. What this says is that if I want to extract raw ore, let's say I can get 1 kilogram per 20 milliwatt hours, or let's say megawatt hours, that's a lot, then it would take 1/10 of that. So 1 watt hour, 20 watt hours would convert to 1 in order to recycle it. Nearly 2/3 of all aluminum beverage cans in the US are recycled. When I first saw this stat, I was like, wow, that's actually a lot higher than I thought. And then I checked on it. The number's actually gone up a little bit since this, now that recycling is a lot more prevalent in neighborhoods. Like for us, it's, you throw everything into one bag, it ends up getting recycled. Other metals that are commonly recycled: platinum, gold, copper, lead, iron, and steel. So iron, steel being, well, steel is a refined version of iron, but those being the most common metal. Obviously platinum and gold, because they are precious metals. So platinum is one of the rarest compounds as far as metals go, but it's extremely valuable, not just because you could make jewelry and things like that out of it, but it's very valuable because of its properties of being resistant to oxidation. And because of that, platinum has a lot of industrial uses. The same thing with gold. Gold is used because it doesn't oxidize readily. And so obviously there is a major, jewelry component to it, but a lot of it is because there is an industrial use for it. Gold is used as a really powerful semiconductor. So substituting new for old materials, this reduces metal consumption by using new materials and new technologies. So plastic pipes in place of metal pipes. We had the plumbing redone in our house, and one of the things that they did was, what had happened was our sewer had backed up into our house, so we had to have people go through and sterilize our basement because it was filled with sewage. And then after that was all sterilized and cleaned up, then what ended up happening was we needed to get our sewer replaced, and to get like drains and backup valves and relief valves installed on it. So if it did back up, there was a place for it to go other than in our house. And one of the things that happened was they had when they were tearing up our basement floor in order to put in this new pipe, is the original pipe was made out of cast iron. The new one was made out of plastic. So that right there helped out quite a bit. And also there's, there were issues with it. This pipe had been in our house for quite a while, and it was very rusted. Every single time they went to clamp down on it, it would fall apart. So they just replaced our entire plumbing system from the sewer, or from our house, in our house, all the way out to the road, replaced all that with plastic pipe. Fiber optics is starting to be common in place of metal wire. So fiber optic uses glass and wire and wavelengths that pass through glass over metal. Like I use radio. Most of the stuff that I do is metal wire. Now I'm also really big into high-end audio, and many high-end audio will have Toslink, which is Toshiba Link, and it's a fiber optic connection that provides high quality digital signals between components before it translates it to analog to go to either speakers or headphones. So fiber optic is being used in those. Internet service providers are the biggest ones that are using fiber optics, and a lot of ocean cables. So if you look up like the transatlantic cables and things like that, those are fiber optic. And it uses pulses of light in order to transmit data. Metal alloys are used in place of traditional steel. So rather than just using just straight up iron, a lot of times metal alloys are used. A lot of this is to reduce the oxidation that happens with those metals. So stainless steel being an example of that is a metal alloy that combines a lot of other things into it in order to prevent or resist rusting. Geological hazards. So this is kind of going into what I've heard it called geological weather, but a lot of people say that's not exactly the most appropriate term in it. But it is, again, because I'm into amateur radio and I operate on lower frequency bands. You're really prone to getting interference from the Earth's magnetic field and things like that. So earthquakes, these are sudden movements of the Earth crust that occur along fault lines where one rock mass slides past another. Gradual movement is called creep, and when friction prevents creep, the stress builds up and leads to this sudden jerk. So it's a sudden movement of that plate. Frequently occurs along subduction zones. You sometimes hear these called suboceanic earthquakes, where they actually occur in the ocean, and then that energy is dissipated through the water. A tsunami can result from it, which is a seismic sea swell. This is where that energy is transferred up. Once it hits the surface, then it transfers that into a large wave, which then builds as it moves through the water. I don't remember what year it was. It had to be 2006 or 7. There was a tsunami that ended up hitting Indonesia, and then there was the tsunami that hit Japan in the 2010s and caused the Fukushima disaster. Volcanoes are another one. Volcanoes and undersea magma vents are the source of most of the Earth's crust. Many of the world's fertile soils are weathered volcanic material, but they they have a human and environmental danger associated with it, like volcanic ash. That's not great to breathe in. There's also mudslides that can result from that. Sulfur emissions is really bad. It can actually cause a lot of water sources to turn into sulfuric acid and become corrosive. You want to see a volcano movie? There's one called Dante's Peak. It's like a really poor quality movie. Like it's a good quality movie. It's just a really bad movie. But it does talk a lot about like volcanic activity and stuff. It's more of an action movie, while like the first half hour of it is more of like the scientific part of it. And it's your stereotypical 90s science movie where scientist comes in and is like, hey, you should be warned about this. And then the population is like, shut up, you don't know what you're talking about. And then of course, then it's just a volcano wreaking havoc on the area. Landslides, these are actually a lot more common than you think. They don't really get reported as much unless they cause major devastation, but this is a general term for a rapid downslope movement of soil or rock. Many human activities such as forest clearing or building homes on steep, unstable slopes increase the frequency and damage done by landslides. When I was in the Navy, my one of my last deployments was in 2010 to the earthquake that happened in Haiti. And the reason that that was so bad is because the city of Port-au-Prince was built on a hill, and when the earthquake hit, it caused the city to kind of slide down that hill. So to kind of summarize what we went through, we talked about some tectonic processes, rocks and minerals, economic geology and mineralogy. So talking about strategic resources, which are resources that if they're cut off can provide or can be detrimental to a country. The environmental effects of resource extraction. So the big one we talked about was different types of mining and how to restore those mine, how to conserve geological resources through recycling the materials, and some geological hazards that occur. And then here's a picture. This is Mount St. Helens after it erupted. So this did come to a peak at the top, and then afterwards there's actually a massive crater in the top of it. But that happened 40 years ago and one day. So it happened on May 18th. This is being made on May 19th. So if you see this in the future, obviously adjust. But Mount St. Helens was a big disaster. There were actually people out there taking pictures of it the day before. And if you look at pictures from the day before, it looks peaceful. And then there's a lot of satellites that orbit the Earth. Obviously, there's some with cameras on them that do that actually do like weather photography, and they take pictures in different wavelengths in order to see different weather patterns and things like that. It's used to like track storms, and they actually have one that where people downloaded pictures of this thing, because you could download it with regular amateur radio equipment and download these pictures, and you could see just how high these went. This cloud actually went 15 miles up into or 15 kilometers up into the air, so it was pretty crazy. But it was an event that happened. So that is everything that I have. I'm gonna be moving over to Google Meets after this. Hopefully everyone did well on the AP exam. If you have any questions about it, let me know. I know that the AP submission process isn't exactly the greatest thing, but I'll head over there to Google Meets to kind of answer your guys' questions about it. Thank you everyone for watching.